Built to fail? It's a question that seems absurd when you look at these marvels of modern engineering. They are the colossal machines that shape our world, monuments of steel and hydraulic power, designed and constructed by the brightest minds to perform Herculean tasks with astonishing precision. Every component is stress-tested, every calculation is double-checked, and every operator is trained for countless hours. These machines are not just built to work, they are built to endure, to withstand immense forces, and to operate at the very edge of what is physically possible. They are designed to handle unimaginable tons of material, to move mountains, and to raise cities from the ground up. But what happens when the trust we place in them is shattered? When one single seemingly minor mistake in a long chain of complex operations triggers a catastrophic failure? In those terrifying moments, these titans of industry don't just fail, they transform into agents of chaos and destruction. From towering cranes that delicately lift and place entire bridge sections, to powerful excavators that can scoop up cars as if they were toys, to gargantuan tunnel-boring machines that chew relentlessly through solid rock deep beneath our feet. They are the unsung heroes of progress. These machines are the very backbone of our civilization, the silent, powerful partners behind every skyscraper, every highway, and every dam that powers our lives. We depend on them to perform flawlessly, day in and day out, operating under the assumption that they are infallible. But they are governed by the unforgiving laws of physics. And, when those laws are ignored, even for a second, the consequences are immediate and devastating. The physics always wins. It rarely takes a perfect storm. More often, it's a simple oversight, a critical miscalculation of weight or balance, a moment of human neglect, or a hidden material defect. That's all it takes for these multi-ton steel giants to lose their battle with gravity and come crashing down, leaving behind a trail of wreckage and questions. Today, we are investigating 12 jaw-dropping engineering failures. We're going to break them down, frame by terrifying frame, to understand exactly what went wrong. We'll analyze the immense forces at play, trace the chain reactions that led to disaster, uncover the hidden structural weaknesses, and examine the critical human factors that are so often the root cause. This isn't just about watching things break, it's about understanding why they break so we can learn from the mistakes of the past. Give me the next 10 minutes of your time, and I promise you a fascinating look into the world of mechanical engineering and forensic analysis. You will not want to miss the incredible story of the runaway tunnel borer at number 3, or the shocking chaos that unfolded on the airport tarmac at number 9. So grab your hard hats. Let's get into it. The lattice boom crane is a titan of the construction site, a marvel of engineering designed for one purpose, lifting immense weight with precision. On this particular morning, everything appears by the book. The crew is preparing to hoist a massive precast concrete slab, a routine but critical step in the project's timeline. The air is calm, the team is experienced, and the machine seems ready for the task ahead. But then, something almost imperceptible happens. A slight shudder runs through the boom's intricate steel lattice. To an untrained eye, it's nothing. To a seasoned operator, it's a cold knot in the stomach. This isn't just a vibration from the engine, it's the structure itself crying out. In an instant, that subtle warning escalates into catastrophic failure. The wobble transforms into a violent, sickening fold as the boom buckles under the load. The high-tensile steel cables, now shock-loaded, snap like threads. The concrete slab, weighing tons, is released from its hold and plummets to the ground, erupting in a cloud of dust and debris. The investigation points to a trifecta of deadly errors. The lift was likely overweight, exceeding the crane's capacity at that specific boom angle, but the critical mistake was side-loading. The rigging may have caused the load to swing, or it was dragged sideways, introducing lateral forces the boom simply wasn't designed to handle. A crane boom is incredibly strong in compression, but fragile when bent. This is why the load chart is non-negotiable. It is the crane's Bible, defining safe operational limits. Every component, from the slings and shackles to the hooks and pins, must be meticulously inspected before every single lift. These aren't just best practices, they are the laws of physics written in steel and ink. Ignoring them is a gamble you can't afford to lose. You can't eyeball physics. A controlled release turns catastrophic. A radial gate rips free, unleashing a wall of water. This isn't a leak, it's a flash flood threatening communities, farms, and infrastructure for miles. Constant pressure, corrosion, microscopic cracks, unseen until a critical point. Without non-destructive testing, failure is inevitable. Routine ultrasonic scans, controlled cycling, and timely reinforcement aren't costs. They're what prevent billion-dollar disasters. A TBM is a horizontal skyscraper, hundreds of feet long, billions at stake, eating Earth with a rotating cutter head. Then Bertha stops, jammed deep below, costs exploding by the day. The root cause: misinterpreted ground, hidden boulders and variable soils overload cutter motors and damage the main bearing seal. The fix? A costly rescue shaft. The lesson? In tunneling, the enemy is the unknown. Get the geology right before you cut. A synchronized jacklift loses pressure on one side, and the span lurches. Unbalanced weight twists the structure, potential energy released in a destructive burst. A single seal or valve can fail faster than software can react. You need redundant hydraulics, mechanical lockouts, plan B, C, and D. This happened off traffic, but on an active lift, the public risk is enormous. Redundancy saves more than steel. On uneven muddy slope, a full bucket outstretched pushes stability to the edge. A quick swing downhill shifts the center of gravity past the tracks, and 50 tons go over. Slopes shrink your safe zone. Blind spots hide soft ground. Walk the site. Measure the grade. Heed tilt warnings. Physics doesn't bargain. The most important safety feature isn't on the machine. It's in the operator's head. Know the ground. Respect the limits. A crane rolls along the quay while a ship departs, the crane boom still extended in the ship's path. No horn, no radio call, then impact. Steel tears like foil. Different teams, one channel, departures announced, booms stowed, brakes set, confirmations read back. Protocols prevent collisions. In complex ops, the most critical equipment is the radio, and the skill to use it with disciplined checklists. 800,000 pounds of truck, and as much rock, picks up speed down a steep grade. Retarder overwhelmed, grids overheat, service brakes fade, the truck can't make the turn. Electric wheel motors become generators, dumping energy as heat. Mechanical brakes finish the stop, if they're cool and healthy. Daily inspections, prompt repairs, low gear descents, and emergency ramps. In a world of giants, gravity is the boss. Respect it. A rig weathers monster waves and hurricane winds. The derrick enters dangerous resonance. A critical joint gives. Hundreds of tons collapse in seconds. Storm loads can exceed design, and unsecured equipment can trigger cascades. Procedure matters when nature spikes the graph. Continual structural analysis, reinforcement, and early evacuation protocols turn a financial disaster into a survivable one. 1,000 times a day. Hook, confirm, push. Then the link fails, and the aircraft is unguided with momentum. A slow drift becomes a multi-million-dollar collision. Shear pins protect nose gear, if they're the right ones, inspected and correctly installed. Mandatory checklists and redbacks prevent the worst 30 seconds of your month. Silent giants, until a multi-ton blade rips free, flung by centrifugal force, scattering composite shrapnel. Dozens of high-tensile bolts endure cyclic loads. One failure overloads the rest, or a hidden composite defect lets go at the root. Strict inspection intervals, torque verification, ultrasonic checks, especially in remote sites where the debris footprint is bigger than you think. A robotic arm full of wet concrete. Forces are extreme when fully extended. A joint or cylinder loses support, and the boom scythes down. Hydraulics fail, or the setup does. Soft ground or bad cribbing shifts the center of gravity past limits. Assess ground, use proper cribbing, level perfectly, post a spotter, and keep eyes on hoses, pads, and cracks. Oversized loads demand perfect planning, because even a gentle turn loads every weak link. Overloaded axles, underrated or under-tension chains, inertia finishes the job. Calculate axle loads, specify chain grade, and count. Plan the route before the engine turns. The driver's inspection isn't paperwork, it protects everyone else on the road. We've just witnessed 12 stark reminders of what happens when immense power meets a single point of failure. These aren't just stories of destruction, they are case studies written in twisted steel and shattered concrete. Each event represents a moment where the complex systems we rely on, mechanical, geological, and human, broke down with catastrophic consequences. From the delicate balance of a crane to the unstoppable momentum of a runaway mine truck, the line between a productive day and a disaster is terrifyingly thin. But we don't look back simply to gawk at the wreckage. We study it. We learn from it. Every failure is a critical data point in the ongoing mission for greater safety and reliability. Forensic engineers can read the story in a shear fracture, a corroded bolt, or a warped beam. That mangled metal tells them exactly what went wrong, allowing them to redesign components, rewrite procedures, and build better, more resilient machines. This is how progress is made, by confronting our mistakes head-on. If any of these stories resonated with you, show your support with a like and subscribe for more deep dives. And I want to hear from you in the comments. Which of these 12 failures hit hardest, and why? Always remember, heavy equipment builds our world and saves lives, but only when operated with the respect it demands. Specifications are not suggestions, they are hard-won lessons. Trust your training, trust your team, and never stop asking questions. Stay safe out there, and I'll see you in the next one.